Okay, so hello everyone. Hello everyone. So since I'm the only local member of the committee, it was somehow decided that I would be in charge. So welcome to everybody, and I propose that we start right away. And so Ivan, you will have 45 minutes to present us the results of your thesis, and then we will follow up with questions.
So, finally, thank you very much. It is the D-Day, the H hour, the M minute. Thank you very much everyone for coming. Thank you very much everyone for joining. Today I would like to speak about some results which I obtained for my PhD during the last years. And during this talk, I will present a few contributions to the study of the number of rational points on curves of finite fields. We will start with a very brief introduction, and after giving a list of few results which made the biggest influence to me, that motivated me to start the research, I will define the context for today's talk. This is basically what is written in chapter 3. And then we will discuss the results of chapter 1 and chapter 2, the existing bounds on the general of curves. We will proceed with some preliminary theoretical results on the binary codes which were introduced in chapter 3. And finally, we finish with some preliminary computational results. The main question is very simple. Each algebraic curve defines a pair of non-negative integers, the number of rational points, genus, and obviously there is a Serre bound on the number of rational points. But in my research, I fix the number of rational points. So instead, the only information that we get is the lower bound on the genus of curves having exactly n rational points for finite field. And the question can be stated in a very simple way, in a very general way. Given a pair of non-negative integers, it is possible to find a curve which realizes the pair. This question, of course, counts many years of extensive research. The very famous case is the itenability of the upper Serre bound on the number of rational points, the study of existence of curves with many points. But in my research, I take the point of view of introduced in works of Ivan and Steiner. I consider the set, given the finite field, given some non-negative integer n, we consider the set of general curves defined over the finite field, which has exactly a few rational points. Clearly, this set is contained in the line which is defined, which is defined by the Serre bound. And the first result that really impressed me when I started to dig inside the arithmetics of curves over finite fields, it was the existence of pointless curves. And when I saw this direction, when I saw some papers in the literature, when I saw some results around this existence of pointless curves, I immediately understood that this is what I will do, because obviously it will more easier than the existence of pointless curves, or the existence of curves at the main points. And some of the results, which in my opinion most important, is that when the genus is fixed, there are only few results, because few results for very small genera. When we fix genus, we can up to 4, 2, 3, or 4, and we can classify all finite fields over which the genus G pointless curve exists. But instead, we took another approach. Instead, we fix the number of rational points that genus I. And also, we fix them. We considered the existence of pointless curves over fixed finite field. And the main result, which the result, one of the first results which inspired me to start this PhD project is the result of Baker and Glass. They provided some few bounds on the genus of pointless curves. And in the first chapter, we improve out these bounds. We provide explicit constructions in order to establish a linear lower resistant bound on the genus of pointless curves when the finite field is of code characteristic. No doubts, there is a very powerful result, in my opinion, from Barr and Stein. We can say that the general field, general perimeter curves, for each finite field, for each number of rational points, they prove that there are not only infinitely many genus G curves over FQ having exactly n rational points, but they construct curves non-explicitly, but of consecutive genera. In chapter 2, we provide a result of similar type, but we restrict ourselves on the case of hyperelliptic curves. So, in fact, we are dealing with a very specific case of the same question, and it is not surprising that restricting our consideration of such a simple family of curves, it is possible to achieve a slightly better result, but only for very, very few number of rational points visible. So I would like to move to the content of chapter 3 and describe the correspondence between the world of hyperelliptic curves or finite fields and F2 modules. Since we are working over finite fields of closed characteristic, each hyperelliptic curve can be defined by a very simple model, plane model. And in order to define a smooth curve, I mean, when we write the equation y squared equals f(x), we of course mean the realization of the projectivization. But in my research, we can actually restrict ourselves to the set of square-free polynomials considered up to multiplication by a square in the finite field. And for simplicity, clearly that a hyperelliptic curve is a curve, and it has a genus, it has a number of rational points. Today I will not consider the genus as the measurement of the complexity, and etc. It would be very convenient to think about the genus of high-fidelity curve just as a simple arithmetical function of the degree of defining polynomial. And for the number of rational points, it's very well known that high-fidelity curve is reviewed by two affine models. And in order to count the number of a few rational points on high-fidelity curves, it suffices to solve two affine equations. And so finally, the main question can be reformulated in terms of the set of square polynomials. Once again, we find an actual multiplication by a square in the finite field. So given a pair of non-negative integers n and g, is it possible to find such a polynomial from a square-free polynomial, which defines a curve, having exactly over the cube, having exactly n rational points, and genus G. The first step towards the correspondence between high-fidelity curves and F2 modules is to observe that the structure, the set of square-free polynomials, it admits a structure of F2 module. Clearly, that given two square-free polynomials, it is easy to construct another square-free polynomial just by taking the square-free part of the product. But in this case, we destroy a piece of important information, the leading term of the product. And since by definition square-free part is a monic polynomial. So instead, we simply remove the greatest common divisor of this polynomial. And by doing so, we preserve the leading coefficient. And it is not difficult to see the structure of F2 module on the set of square-free polynomials, since under this operation, each non-trivial element has order 2. Thus, the set of square-free polynomial is actually an infinite F2 model with the basis given by all reducible polynomials and a fixed non-square, a primitive element of finite 2, for example. It is also some convenient to think about the chosen non-square as the only reducible polynomial of GP0. The correspondence between high-fidelity curves and F2 models is established by considering the additive version of the quadratic character of the finite field. The quadratic character is, of course, a homomorphism of multiplicative structures, but the image of the quadratic character is an abelian group of order 2, which, as you know, is isomorphic to, it can be written in additive notations, and the isomorphism is given by a discrete logarithm. So the additive version is also a group of homomorphism. It sends product to the sum, and but the problem is that the quadratic character, I do not define it on zeros. But also, I would like to extend it to polynomials. So, in order to proceed, I must be very careful. So, first of all, in all my constructions, I have to choose the set of admissible roots of polynomials. So, we start with fixing a subset in the finite field, and we have to change the data a little bit. Instead of the set of square-free polynomials, we must switch the consideration to the set of square-free polynomials such that it may have roots only inside of S. And finally, the correspondence is given by the composition of the additive version with a relation map. But as you can see, we allow the relation process only on the elements of the finite field outside of the chosen S. So the notations presented here in the end, but it can be thought like a vector actually in a space in a vector space F2 of Fq minus S. It is an F2 model with the alpha Z Fq minus S. This is also a vector space whose coordinates are indexed by the chosen alphabetic elements. Since we started with an additive version, the additive version of the quadratic character, it involves this logarithm. We know that it is a group homomorphism. All these properties, these chi-star S maps, they share properties, the same properties. It is, in fact, a homomorphism of F2 modules. It says the product to the sum. It is a homomorphism of infinite dimensional, from an infinite dimensional F2 model to finite dimension. And we know the basis of this infinite dimensional F2 model. It is essentially the same basis, but we simply just remove from the consideration some polynomials of degree 1. And the first feature of considering such maps is actually now we have a closed formula to the number of, for the number of rational points on such curves, on high-fidelity curves. The only thing we need to do, if we are given with a high-fidelity curve y square equals f of x, where f of x is a square polynomial, in order to count the number of affine rational points, it suffices to know the set of roots of this polynomial, of the finite polynomial, and the relation, the chi-star S vector of this polynomial. And speaking for the number of rational points at infinity, it is just an arithmetic function of the leading coefficient, of the degree, just another set of parameters. There are very specific examples of polynomials which have no roots, and such, which are non-trivial. They are square free, and they have zero chi-star vectors. Such polynomials, we will see that if they have even degree, they have maximum possible number of rational points that high-fidelity curves may have, and by taking quadratic twists of such curves, we simply negate all the data, since we are working with binary objects, and we give, and by doing so, we can find pointless curves. Here is a very quick demonstration of how chi-star S maps work. We are dealing with a polynomial who has some leading coefficient, who has some roots, some other irreducible divisors. And in order, let's assume that we want to find the number of rational points on the associated high-fidelity curve. The number of rational points at infinity, it is very easy to count. It is just 1 because the degree of the polynomial is odd. But for the number of rational points, we can compute chi star s of f of x. So in order to do this, we have to choose, we have to understand that okay, there are two rules, 1 and 2. They are not allowed. We consider the corresponding F2 module with alphabet F5 minus s. There are 3 coordinates, and we can compute chi star vector of f of x in 2 ways. Directly, or we can compute chi star vectors of, for example, each irreducible divisor. And it's very easy to see that the sum of the vectors which correspond to the irreducible divisors is exactly the chi star vector of the original polynomial. And it is very easy now to compute, easy, give you the evaluation, but it is very easy to compute the number of affine points. So, first of all, we are going to understand some results. We are going to speak about the existence of pointless curves. And as I said, if we would like to construct a pointless curve, a pointless hyperelliptic curve, we will have to start with a subset of the finite field. And in the case of pointlessness, we will have to start with the empty set. So now we move to the left. And the main result of the first chapter is exactly existing lower bounds on the genus of pointless hyperelliptic curves. The idea has been described a few slides later. All we need to do is to present a square-free polynomial of even degree, monic, which has chi star vector equals to 0. And in chapter 1, we do this for all genus that we want to consider, and we do this explicitly. In this theorem, we also considered a little bit the case of even characteristic, but in today's talk, I speak about only odd characteristic for simplicity. Now we have to take the right path, because I would like to present the results of chapter 2, and there we would like to study existing bounds on the genus of curves having some positive number of rational points. And once again, we have to start with a probably non-empty set and to consider hyperelliptic curves with the following form. So we have to consider square-free polynomials with prescribed set of roots. And the consideration of some roots, so bringing some roots into consideration, it aims to achieve some results as follows. The main result of chapter 2 is just an existing bounds, quasi-linear lower existing bound on the hyperelliptic curves of finite fields. So for all admissible number of rational points, we manage to find a polynomial, to find a curve C, which has exactly n number of rational points, exactly n rational points. And we also consider the second guy, the family of pointless curves of consecutive genera starting from some constant, which is defined by Q. And we do this in such a way in order to produce a family of curves which have exactly n rational points of consecutively increasing genus. The proof is very technical, as far as I know. In chapter 3, we start to develop the ideas from chapter 2. So, in order to dig a little bit more inside to the question, we would like to understand: is it possible to find another methods or another bounds, maybe for only small finite fields? And so here, what is going on? In chapter 3, we are trying to understand what is happening below the bound presented in chapter 2. This typical question mark. But for the moment, as it's a research project, we don't have a lot of theoretical results, but we have already computed something for small finite fields. It looks like, by considering this correspondence between high-priority curves and F2 models by means of linear coding theory, the corresponding machinery, heuristical algorithms, it is possible sometimes to almost achieve the survival. It is very easy to define fold. Let's consider once again the K-Starless map. So we start with the finite. We start with the subset in the finite field. We have the introduced homomorphism of the F2 models, and we essentially know everything, and we introduce the monster codes as the kernel of these homomorphisms. And I would like to emphasize that this is also infinite dimensional F2 model, and in order to, but in practice, we choose a finite submodel by fixing a finite number of elements from the alphabet. And so very soon we will make a choice. The first question when you see such incredible constructions of infinite dimensional F2 models, most probably it is reasonable to ask why. Why do we consider this? And the idea behind all of these constructions is to consider the elements of all these binary codes as relations between chi-star maps of the irreducible polynomials. By design, the elements of the codes, they are considered as bit masks. For each relation, we can define corresponding polynomial as the product of some reducible polynomials. And the idea is that the chi-star S vector of the product is a zero vector. And for example, if S is empty, as we have already seen above, it gives a way to construct sometimes curves without rational points at infinity, for example. But if the degree of the polynomial is even, it is possible to construct pointless curves. And speaking about the more general case, the case of a positive number of rational points, for example, it suffices to understand what is going on inside of the cosets of such codes. Since the multiplication by polynomials having zero chi-star vectors, we essentially do not change information on the number of finite rational points. So by doing so, we have an opportunity to control other parameters, like the degree, the genus, the relating theorem, etc. And the choice that we do, that we make, the choice of the finite subset of the alphabet that we make in chapter 3, it's very simple. So for the alphabet, we just choose the set of degree 2 monic irreducible polynomials, I2. And in the corresponding finite dimensional code, I call them also pointless code, can be understood it appears that we can say some, we can understand some information on these codes. So, for example, we define this code by parity check matrix. We compute all chi-star vectors of each irreducible polynomial, and here I prefer to write the vectors in columns. And the first result that we obtain is that actually we know the dimension of this code, or equivalently we know how to compute the rank of the parity check matrix. And this result can be obtained by bringing into the consideration the action of the group of affine transformations and transformations of the affine line. The beauty of these guys is that they act on irreducible degree 2 polynomials, one simply transitive, but they also act on the elements of finite group two transitively. And since we construct the parity check matrix written in columns, we use evaluation maps. The rows of the parity check matrix are indexed by elements of the finite field. So we have the action of the affine group. And we also know that there is action. Polynomials from I2, they index the columns of the parity check matrix. We also have action of the affine group here. So it looks like we found ourselves working in a very nice situation. And for example, what is the idea behind computation of the rank of the parity check matrix? Let's consider the vector space spanned by chi-star vectors of irreducible degree polynomials. It is the columns of the parity check matrix, and this vector space is a J1 invariant space. We know that this group acts two transitively. We know also that sometimes the order of this group is divisible by 2. So it's not really clear how to work with the modular representation theory here. But hopefully there is a classification of invariant spaces. So this is why we know the rank of the parity check matrix and the dimension of the code. And obviously we know the degree of the code, which is just the number of degree 2 polynomials. computations, we consider in this talk only the case of prime fields. This is due to the fact that we also can say a little bit more about the parity check matrix and thus about the codes. After a suitable numeration of elements in the finite field by lexicographical order, and thus it also gives nice numbering of elements of IT. We can write down the parity check matrix as the sequence of symmetric circular blocks, and by computations, by magma, it is possible to prove by means of theory of cyclic codes, since the rows or the columns of each block, they define a cyclic code, and it is not. It's very easy to compute the dimension of the results in space. So computationally, we can prove that the rank of the entire parity check matrix is actually the rank of any block. These can be used in practice in the following way, for example. So on the left side, we have ordered set of irreducible to polynomials, money, of course, and the matrix in the center is exactly the parity check matrix. Here, each row corresponds to the chi-star. It is the chi-star vector of the corresponding polynomial. And as you can see, we have three blocks, for example, here. This circular and symmetric matrix, each block. And we also know. So what is the idea behind? Is that we can use the fact that we know the rank of each block. It coincides with the rank of the matrix. And just imagine that we can ask magma. We can take a big prime number. We can compute somehow the parity check matrix, and we can ask magma to compute the corresponding pointless code in order to understand. In order to obtain some pointless curves, for example. But this will take a lot of time, a lot of memory, and this is not a good idea actually. So instead, it is possible to reduce the computations to do this efficiently. We know that the rank of the last block is coincides with the rank of the entire parity check matrix, and it gives a very nice idea how to compute the basis of the pointless code. In the reduced row echelon form, equivalently, we can compute directly the redundancy set. So we know what is exactly the information set of the corresponding code, and we can remove it from the consideration. This allows to store in memory only the redundancy part of the pointless code, and it significantly facilitates the task of the search of pointless curves, for example, or by using classical Zimmermann like algorithms and its modifications. We also know that since the Pogildiakov matrix is constructed by circulant blocks, we also know that we are working with the pointless code is in fact quasi-cyclic code. So I expect that there are more modifications can be done with the computational approach. There are several ways how to reduce the complexities also. And the first idea, actually, it comes from the results from the paper of Pogildiakov and Top, going back to the existence of genus 3 and 4 pointless curves. It was a very good idea, actually, to consider fixed subcodes. And it is possible to prove that in the case of prime finite field, the pointless code is actually the sum of two fixed subcodes. They can be fixed by order 2 elements, by 2 evaluations. It is each element from each of these fixed subcodes. It is also some relation, but instead of working with irreducible degree 2 polynomials, we will have to work with products of orbit elements under the action of the corresponding rules. But this will help to save a lot of resources. There are also several crazy strategies, but unfortunately I cannot explain all of them. The first preliminary result that we can provide is that we can simply construct these pointless codes for small finite fields and to run the search of minimum code words, for example. The pointless codes, the elements of pointless codes, they give product of degree 2 polynomials only. So if we take W degree 2 polynomials, and the product of W degree 2 polynomials distinct, it will give us W minus 1 genus pointless curve. So it is very easy to understand the genus of the resulting product. And it looks, so we did some computations for small finite fields, and it looks like we reach some bound for some finite fields. And we also, we of course can continue this table, but we do not have space. Anyway, let's consider pointless curve, pointless codes, pointless code for Q equals 97. We will have to deal with the incredibly big code of incredibly big length, degree, and the dimension. And as I said, there are several crazy strategies. They help to reduce complexities of computation, for example, the weight spectrum of this code. It is possible to compute the weight spectrum of this code explicitly, and it is presented here. It is a symmetric set, and it contains only odd numbers, and it starts from 8. We managed to find examples of. Okay. We managed to find examples of pointless curves, and I think the most incredible achievement for this finite field is that we managed to find a pointless curve of genus 7, which corresponds to the minimum vector in this pointless code. can be done. So the third bound, it gives the following information, that if there is a pointless curve or F97, that it has genus at least 6. So I would like to finish my talk as well as my PhD project with a very humble question: is this bound sharp? Thank you very much for your attention.
Okay, thank you for your talk. So we step to the next round of this PhD defense and ask questions. So the tradition is to start with the referees, and so I propose that we start with Yakov, which is the referee, which is the first way. Yeah.
Okay, well, first of all, Ivan, thank you very much for your talk, which I found very interesting. So you answered, you stopped at the end with the question. Do you have a guess what the answer should be?
I want to believe. I want to believe that.
Who believes you?
Unfortunately, to this very moment, I cannot prove a lot of things. But I believe, I want to prove one day that there are curves. It is possible to find pointless curves, even for a, I'm ready to simplify, even for a prime finite fields only, maybe. I hope it will be possible to prove that there are curves of genus around square root of P.
Around square root is still a little bit big. Anyway, so let's continue. Yeah, an important thing here is, of course, that you work with hyperelliptical, and moreover, in much of your work, you work in characteristics of.
Excuse me. Ah, okay. So.
Okay, we continue.
Yeah.
So, yeah, there are these two important facts. Of characteristic and hyperelliptic. So I will not immediately move away from hyperelliptic, but your method of the chi-S star, can you conceive an analog in characteristics?
Yes.
Okay, so can you give a description how such an analog looks like?
So we are speaking about hyperelliptic curves in even characteristics.
Yes.
The recipe is as follows. We consider rational functions and trace maps.
Yes.
It will require some work to achieve similar properties as in a characteristic that we get for free. But unfortunately, in characteristic 2, we do not get some things for free. I did a little bit. I tried to make research in this direction. It is possible to do something. I would like to know that it will take some work to. I'm trying to remember. We will have to struggle for smoothness, this is what I want to say. Yes, because as far as I remember, we will have to solve a system of equation, which is intersection of the degree two surfaces. And since we are working with characteristic 2, it will be possible somehow to reduce nice to get nice conditions for smoothness also.
And would it help to restrict the input? Maybe if you would take the anti-triad approach, so only the y squared plus y equals a polynomial. Would that work? And then have some form of additive group of polynomials?
Instead of polynomials, we will have to consider rational functions. Y squared plus y equals a rational function. And we will have to split this rational function by simple procedure to the sum of functions which denominator is the power of some irreducible polynomials. And we will have also what I call the locality of smoothness. We will have to consider smoothness locally for each irreducible divisor in the denominator separately. It is possible to introduce this, to consider trace maps instead of quadratic characters. But essentially it is the same. We will have to struggle to prove that there is a choice of rational functions in order to get a smooth curve. We will have to struggle to understand that actually there is a rational function which has this trace star map, trace star vector of good Hamming weight, for example. But computationally, it is a disaster because these sizes of vector spaces to consider, it grows too much because we will have to bring into consideration a lot of rational functions.
Okay, I see. And one last question. So in the last bit of your lecture and also in the thesis, you restrict to irreducible quadratic polynomials. And so your example in characteristic 97 is also by having a product of a lot of quadratics. I can understand why, for quadratics, that you have most access to what the Frobenius group of the affine transformations do. But did you have a look at what happens if you extend the degree slightly?
Suppose let's change the degree from 2 by whatever we want. Let's, for example, take any irreducible polynomial of degree d. Let's consider the orbit under the action of the affine group, and let's once again consider the parity check matrix. By considering the spanning space, we will get again invariant subspace. We will know the dimension. We will be able to make similar computations in order to get, for example, an example of curve with given number of rational points, or example of curves without rational points, maybe. Because it is very important at some moment to struggle correctly with the problem of choosing correct degree, because we will have to struggle at some moment for the genus. This is exactly, I take only degree 2 polynomials because it is somehow easier here. We get very simple arithmetical formulas.
I agree, I expected this. Okay, thank you.
Thank you very much.
Okay, thanks. Yeah. Now, I would suggest that Marc Perret asks these questions.
Okay. Hello.
Hello.
On a un petit problème, so.
we are experiencing these technical difficulties.
On n'entend pas très bien.
Il y a qu'un entre deux.
Oui.
Delphine, vous entendez là?
Oui, oui, là c'est bon.
Bon.
Vas-y, parle. Ah, il y a un problème. On t'entend pas.
Il y a un problème?
Oui.
Si, on entend.
Si. Ah oui, bien. Il a parlé entre temps. Essaye encore une fois, parce que de temps en temps j'ai l'impression de t'écouter. Vas-y.
Et donc, là j'essaye.
Ça marche.
C'est bon?
Ouais.
Non, non, t'es coupé de temps en temps, il y a un problème.
Ah zut.
On entend là.
Vas-y, essaye encore une fois de poser la question.
Là c'est une collection.
Est-ce que les autres participants à ces listening
Ah. Est-ce qu'il y a un autre participant? Est-ce qu'il y a d'autres micros qui sont activés? Non, c'est bon. Hein. Tout le monde a coupé son micro. Qu'est-ce qu'on peut faire?
Tu peux pas la faire? Ça marche pas mal par
Non, mais tout à l'heure ça marchait bien.
Ah oui, quand on a fait le test, ça allait.
Ouais, mais là on l'entend bien.
Mais on t'entend bien maintenant, c'est juste que de temps en temps, quand tu parles, tout à coup t'es coupé. Essaye encore une fois.
Dès qu'il commence à parler de maths, on n'entend plus.
Oui.
Dès que tu parles mathématiques, c'est coupé.
En fait, il faudrait peut-être changer le micro, enfin changer le haut-parleur. On pourrait le mettre sur un haut-parleur de Mac, même si c'est pas vraiment bon.
Ok, ben on va se mettre sur le haut-parleur de Mac.
On peut
Du coup,
essayer ça.
Yvan, il faut que tu reviennes devant. Là. On va utiliser le micro de l'ordinateur. C'est ce que suggère.
C'est le haut-parleur, c'est le
C'est
haut-parleur.
plutôt le haut-parleur que
C'est le haut-parleur qui est gênant.
c'est avec les deux.
Alors c'est mieux là ou pas?
Je sais pas, Marc, tu pourrais dire quelque chose de moi?
Ah non.
Mais voir à fond ton son pour voir si.
Ouais, et donc tu amplifies avec le son.
J'arrive pas à modifier mon son. Ah, désolé. Audio. Alors le son à fond. Comme ça, là je suis à fond. Hein.
Ouais. Marc, est-ce que tu peux parler, s'il te plaît?
Je sais plus où j'en étais de la fontaine, alors.
C'est super.
Et ça marche comme ça?
Ouais, ça marche.
Ça marche. Vas-y.
Donc, merci pour ton exposé. I have only 2 questions, maybe only one, if it doesn't count. Have you tried to overcome the limit of your method? The limit is 2 times 2 plus 2, by considering Vice curves other than the straight line, by considering a Kummer covering of degree 2, quadratic coverings of a Vice curve, other P1 or other lines.
I tried to consider fiber products of hypertrophic curves. I tried to consider, of course, pseudo-elliptic case. But I'm not really impressed by this direction because at this moment I do not understand how to do this correctly. What is the goal? Just to achieve the number of points which is bigger than 2q plus 2. This is a good idea, but once again I would like to struggle. I would like to get the line of consecutive genera. It is not easy because it is. I think that Kummer extensions and fiber products of Kummer extensions of the projective line, I think they do not fit to this goal. I think it is much better to do the following things. Either to completely switch to Artenschreier extensions, as well as the Ambardit with the Schnecktonov, this approach to take, or to use to understand some properties, some data, some information, to get some information on the Jacobians of these curves, of hyperelliptic curves that I consider, in order to provide reasonably good data to the methods of general classical theory. Because I did several computations and using the classical theory is possible by using a lot of examples that I can compute. Sometimes it is possible to find curves with many rational points, with rational points from some big range, but of course it is not easy to do when the Jacobian is a big size.
Okay, thank you. Can I raise another question? Or est-ce que ça va les sons ou
Oui.
ou Karen?
C'est très bien.
On t'entend.
Très bien. Donc, Ivan, I have another question, a technical one. In the proof of your theorem 2.4.1, it is on page 60 of your new PDF.
Let me find it. Okay, I can.
Si tu veux, je te mets la caméra. Attends, je te mets la caméra
You have page 60?
60.
It is the version that you received today?
Oui.
Yes, this version.
Alright. It is around. Okay, I see the proof.
Yes, if you remember, when we had the Zoom
Yes.
together a few days ago, a few weeks ago, you remember, I told you that I have the feeling that you cannot apply your lemma 2.4.3 in case capital N equal Q plus 1 and R equal Q. And it seems that it is not fixed. Maybe I was wrong.
It is not fixed.
I'm not sure, but maybe I was wrong. Or maybe I'm not sure. Do you remember?
Yes, yes.
Capital N equal Q plus 1, then R can be equal to Q, which is strictly greater than Q minus 1.
I think I
cannot apply lemma 2.4.3.
I think there is no really big difficulty to answer this question, but at this moment I cannot remember.
Okay, thank you.
As you want, I think it is my job to contact you after.
Okay.
So there is as far as I remember, there is a remark above in the text which says that we remove from the consideration the case of R equals Q. And as far as I remember, the idea is actually to take as less as possible. Put the minimum necessary number.
Okay,
Yes, I'm sorry.
Okay, merci Marc. So I propose that the next questions will be given by Everett Hall.
Hello, can you hear me?
Yes.
Hello. Yes.
I only have a few questions. One, I guess, going in the opposite direction of Jaap. If you stay in whatever characteristic you want, but instead looked at superelliptic curves, how much of this would carry over?
carry over.
Yeah, how much of the work, could you adapt the work to still succeed in the case of superelliptic curves? So y to the n is equal to a polynomial in f, in x.
I didn't think a lot about this because I left this for future, so I have not a lot of things to say about it. I realize that it will be probably not easy to do.
Okay.
It is clear that we will adopt the idea of taking quadratic characters. We will replace it by another characters, right?
Yes.
We will have here. I'm not sure, so I don't want to be mistaken, but I would like to continue the discussion. We will have to change the base f2 by maybe a ring, not a field. And this maybe will cause some technical issues. I don't know what to expect, but I'm curious. I'm curious to know what will happen. How many problems we will find. But this is our job anyway. And I would love to see what is going on in the future in this direction.
I guess one issue is you cannot get every possible genus
yes,
of these curves.
These curves need much a lot.
Yeah. And one other thing I was curious in your data. So like, I could look in the new version of the paper. The table at the very end on page 79.
Old.
So this is the one where you're saying what genera you get pointless curves at for various values of Q. And mostly you're getting things that seem very close to the lower bound from Serre. But for odd degree extensions of the prime field, it looks much, much worse. And I'm wondering, does that have to do with the choice of using irreducible quadratics? Or do you have any idea why things don't seem to work as well for those fields?
Yes, so the answer is actually lies on the surface. It's just because square finite fields, they are good fields. So I can briefly explain why this is happening, because let's take any finite field, not prime. Let's take a square finite field, for example. We know that there is in the subgroup of commutations of the affine transformations, there is a subgroup of order around square root of q. Square root plus minus 1, right?
Yeah.
So let's consider not the set of polynomials. Let's split the set of irreducible degree 2 polynomials to the set of orbits under the action of such groups. They are very simple, right? Up to conjugation, we take it. We can take just the homotopes, and we will find ourselves working on the same task, on the same problem, but with a reduced code, such thing. In the slides, I considered on a very simple case, but here we are talking about much larger groups. And in fact, for square finite fields, it is not difficult to prove that, and it's known actually, but not in this language, that it will be possible to construct a pointless curve by considering just an orbit of degree 2 polynomial under the action of square root of Q subgroup. It is known result. It is known, but it appears in a weird shape, mostly. I think in one of my texts it is written down. Yes. And obviously, we do not have such a closing situation when the finite field is not square.
Yes.
I mean, it's such a pity. We will have to, I think, the general recipe is to consider the reduction by involutions.
Yes, okay. All right, so the answer is not that the odd fields are so much worse, it's that the even fields are so much better.
Yes, as usual.
Okay, yes. All right. May I ask one more question?
Please.
Yes, please.
So I understand, why the arguments work to make it so much easier to create pointless hyperelliptic curves. I mean, the bound you get on the genus is, significantly better than for curves with just a few points.
Mm-hmm.
And so I understand how that comes from this work, but I'm wondering if you have any feeling about whether that is the truth. I mean, your construction has a harder time finding a curve with 2 points than it does finding a curve with no points. And I'm just wondering, is the bound on the genus actually worse, or is that just because that's the only way we know how to think about it?
The bound for which number of rational points? For positive?
Yes. Yeah. So your bound for no points is, q over the log of q, and your bound for 3 points is, 1/2 q. So, do you think those bounds are actually close to the truth?
No. What I think, I think they are far from the
Okay.
estimate, because we really must have some square root of Q order. I believe so. I don't know how to prove this so far. Right. I believe actually that my expectation is inspired by the results from the fluctuations of the number of rational points.
Yeah.
And one of the last questions that I discussed with Alexei Zekin is that I was just asking him some weird questions. So, for example, let's consider some intervals of existence. If there is a curve with endpoints of genus G, it looks like it must exist a curve of genus G plus 1 of the same number of rational points. Or the same question, if there is a genus G curve with n rational points, then it must exist a curve with n minus 1 rational points. And it looks like, by considering hyperelliptic curves, it looks like this is true, starting from some moment. And this is why I'm speaking about fluctuations on the number of rational points, because in some sense we know what to expect, or maybe I'm wrong. But I believe that these bounds, these linear bounds or quasi-linear bounds from chapter 1, chapter 2, they far from to be nice.
Okay.
I think they are very
good. Good. Thank you very much, and thank you for an interesting paper and a wonderful talk.
Thank you. So the next question I would ask Roger, you know to ask? Roger, Antoine?
Just a minute, yeah. Hello, Ivan, thank you for your nice talk. So actually I have the same question as Everett, but not about super elliptic curves. I wanted to know if you could apply also this for trigonal curves. But,
I didn't even think about it because I would like to avoid a lot of coordinates. Because all of this works nicely, just because we have only one coordinate, and we can use evaluation maps. For trivial curves. I don't know.
I have no more questions.
That's it? C'est bon?
C'est bon, c'est bon.
C'est bon, okay. So, next question, maybe from Nurgadu? Yeah?
Yeah. Just thank you very much for the talk. I almost have no questions. Actually, the first one I was thinking to ask about the encoding of the particular. So they asked you, and what I can ask you now, mostly you are interested in pointless curve. So I think it is asked also how about main points. But I want to actually not ask, you are giving the bonds that the result which depend. I don't remember what I did there. I'm sorry, 10 years passed already, and I was trying to find it what it is. This is more general Q, the bond belongs to all Q multiplied characteristic. I think you remember better than that.
Excuse me, there is a problem with the sound. Are you speaking about your results from your PhD?
I'm sorry.
Yeah, in the case of the lack of points.
Yes, lots of points.
Yes.
You are comparing with your bonds.
Yes.
As far as I remember, for square Q, we have something better.
Yes.
Have you noticed that one?
Not on this talk.
Okay, so what I was suggesting, to get this bond, we were working with main points, curves with main points, using Hermitian curves.
Of course.
Maybe for future work, you might use your curves to paint a better bond for any prime function. Maybe you can think about it.
Yes, actually, maybe. I cannot promise, of course. Anyway.
No, this is just a remark. So, what I was thinking to say, okay, we have a bond, you obtain much better bonds by explicit observation. And then there is another bond for given powers of the characteristic. The reason is we were using explicit curves to construct covering of the curves to obtain curves with many points. But now you also have a curve with many points, actually 2Q plus 2. Maybe you can use that curve to obtain vector bonds for not square fields. I don't know whether it will work. Just a suggestion.
I think, I do not understand everything, but I think one of these questions seems to be written on my blackboard in my office.
Okay. Okay. So sorry, there is no question left from others.
Thank
And
you.
thank you very much for your talk.
Thank you very much for
It was very nice.
this.
Thank you. Now, Marc, Henry, maybe tu as des questions?
Can you hear me?
Yes.
Okay. Well, my question will be very close to the question that has already been asked. You have the impression that, well, part of your work uses really the fact just that there is an automorphism of degree 2 on the curve. And one of the consequences is sort of you get only, well, that if one of the curves have very few points, the twist has a lot of points. mean, if you have an automorphism of higher order, say defined over the finite field, then you could use the twists, and again, you will get that. Well, in that case, it's more complicated because the sort of the average, the curve is q plus 1 points, but you're bound to have several that will have a lot less and several that will have a lot more. So have you tried to play with this?
No. Are you speaking about extension of hyperelliptic curves with many points? Are you speaking about extension with some specific groups? Maybe I do not understand.
Well, that perhaps it would be, well, let's take maybe the simplest case. You have you look at curves with a group z over nz over nz inside the group of automorphism. You might assume that the quotient is pi 1, that is projective line. Then for this family, I have the impression that you can maybe get more. It's more restrictive than super elliptic curves, because I'm assuming that the cyclic group is generated by an automorphism defined over the finite field. So, I don't know if you can carry through some of your technique.
I don't know any. So I didn't try this. This is what I can say first. I didn't try it. So I must see.
Well, maybe it doesn't yield anything new or probably worse trying. The second and last question that I wanted to ask is if instead of looking at sort of two coverings of the projective line, you look at two coverings of something else. So probably the most interesting thing would be to look at maximal curves or almost maximal curves and double coverings.
I don't know. I started my PhD just in order to get rid of any studies of maximum curves. I don't know. And the irony is that actually I had 2 slides prepared with results on the existence of maximum curves. So I don't know. This is funny, but this is not my PhD.
There's plenty of question. It's not
I did some research on resistance, and I got some results. As you know, we communicated around works of Top from this.
Yes, I remember.
And so I'm kind of proven to myself that I can do something. No, it's okay. Let's do something else.
Fine.
But I'm curious to know if some things will work in this case. But not me.
Well, thank you very much.
Thank you.
Ok, merci Marc. Delphine, tu as des questions? So I also have no interesting question for you, but thank you for your talk, and it was very interesting for me to see many mathematics I like representation theory and coding theory appear to solve such a tricky question. It was very interesting. Thank you very much. So if there is no more questions, then our next step would be to start a new Zoom meeting just for the members of the committee, so we can go on with our things. And So you will have to wait the decision and we will have to meet there. Okay, so we get a little interruption here. And please, for all the committee members, now you have to switch to the other Zoom sessions that we have told you. If anybody gets lost, write me an email and we will get you on board again. Okay, so see you in a sec.
Thank you very much for your questions.